Bismillahirrahmanirrahim. My name is Dr. Muhammad Yar, Assistant Professor Chemistry, Department of Physiology and Biochemistry. Title of my presentation is Design of Single Atom Doped Carbon Containing Zero Dimensional Materials for Hydrogen Dissociation through Computational Tools. So let's begin with the introduction. In the modern era, we are facing the challenge of depleting non renewable energy sources such as oil, coal. The increasing use of the fossil fuel also leads to severe environmental issues. In contrast, renewable energy sources like solar, wind, thermal, and biomass offer promising alternatives for a cleaner future. Among these, hydrogen stands out as the most eco friendly fuel, offering a sustainable solution to our energy needs. Hydrogen is a highly efficient fuel because it has very high energy density compared to other common fuels. As shown in table, hydrogen heat value ranges from 120 to 142 megajoule per kg, which is significantly higher than the other fuels like methane, petrol, gasoline, and natural gas. The high energy density makes hydrogen an attractive option for many applications where high energy output is required with a minimal fuel weight, such as automotives and aerospace industries. Moreover, hydrogen fuel cell converts chemical energy directly into electrical energy with water and heat as a byproduct. In contrast, conventional combustion engines primarily produced greenhouse gas along with the heat and water. Available catalysts for the hydrogen dissociation reactions are noble or mostly noble metals such as platinum, palladium, and rhodium. Platinum is considered as an ideal catalyst. However, the high cost and scarcity limits the practical application of the platinum catalyst catalysts. Search for the low cost and abundant material to substitute noble metal catalyst is a major focus in the ongoing research efforts. Types of catalysts. Catalysts come in various forms, each with its own distinctive characteristics and advantages. These forms includes bulk material catalysis, nanoparticle catalysis, subnanoparticle, and single atom catalysis. Single atom catalysis is an advanced technique in the field of catalysis where individual atoms are dispersed on a support material to serve as an active site for a chemical reaction. In the recent past, these materials have gained significant attention from scientific community working on single atom catalysis due to their high electrochemical stability, large surface area, and edge effects. They also possess unique physiochemical properties including optical, electronic, and magnetic characteristics. These features makes them ideal candidate for the variety of applications such as energy storage, sensing, catalysis, and optoelectronics devices. Point of bonding. Currently, the best catalyst for the hydrogen dissociation reactions are based on the noble metals, which are quite expensive and have limited sources. Moreover, noble metals suffer from low stability and high over potential issues. The following softwares are used to explore the structural, electronic, and catalytic properties of transition metal doped zero dimensional materials like Gaussian 09, GaussView 5, Multi WFN, WASP, Quantum Espresso, VMD, and Chemcraft softwares. Level of the theory used in our current studies are B3LAP and Omega B97 Omega B97 XT along with 631 plus GDP level of theory. This slide outlines the computational methodology used in our study of hydrogen dissociation reactions. We start with the geometry optimization to ensure the lowest energy configuration. Next, we perform the frequency calculations to analyze the vibrational properties, which help to confirm the stability of the optimized structures. We then calculate the adsorption energies to understand how hydrogen interacts with the complexes. NC analysis is used to understand the nature of the interaction, while EDD and NBO analysis is used to observe the electronic properties. This study focuses on the transition metal doped zero dimensional carbon material, specifically C20, C24, and C60. Notably, C20 exhibits metallic character while C24 and C60 are semiconductors in nature. So starting with the optimized geometry of C24 nano cage, which is considered best for its stability and catalytic activity. Here we presented the top and side view of the optimized geometry of C24 nano cage. C24 nano cage comprises of 12 pentagonal and 2 hexagon faces. These faces are also ideal for the doping of catalyst. In the next step, we doped C24 nano cage with the first row transition metals one by one, considering 4 different possible spin states for each to confirm their thermodynamic stability. The highlighted spin states are the most stable spin state of each complex, which are further selected for the hydrogen dissociation reactions. Next, optimized geometry of transition metal doped complexes. Here is a pictorial representation of transition metal doped C24 complexes along with their interaction distances. However, the interaction distances between transition metal and C24 nanocages complexes are in the range of 1.88 angstrom to 2.08 angstrom, which primarily reveals the chemi-absorptions between the metal and carbon nanocage atoms. Among the first row transition metal complexes, the shortest interaction distance is observed for the manganese, which is 1.88 angstrom and confirms the strongest interaction of the manganese with C24 nanocage. Adsorption energies of all the complexes are presented in tabulated form. The negative sign of the adsorption energies of transition metal doped C24 complexes confirms their thermodynamic stability. Thus, the highest adsorption energy is observed for the manganese nanocage complex with the adsorption energy of minus 6.22 electron volt. Adsorption of the hydrogen is conducted on all the transition metal doped C24 complexes. Here we present the complexes that demonstrated a noticeable change in hydrogen-hydrogen bond distance upon their adsorption. Hydrogen-hydrogen bond distance lies in the range of 0.77 to 0.93 angstrom. Among the studied hydrogen metal complexes, longest hydrogen-hydrogen bond distance upon adsorption is observed for the manganese complex, which indicates a strong interaction between hydrogen and manganese complex. Optimized geometry of the hydrogen doped complexes. Adsorption energies of hydrogen doped transition metal complexes are in the range of minus 0.05 electron volt to minus 0.88 electron volt, which indicates the favorable adsorption of the hydrogen molecule on transition metal doped C24 complexes. The given figure illustrates the reaction pathway for the hydrogen dissociation. It consists of relative energies of the reactant, intermediates, transition state, and final product. Among the studied hydrogen metal complexes for the homolytic dissociation, the lowest energy barrier for hydrogen dissociation is calculated for the manganese catalyst, whereas the highest barrier is seen for the chromium catalyst. Moreover, the dissociation barrier for the hydrogen molecule over the iron, and cobalt complexes are almost comparable with the difference of 0.06 electron volt. These results show that manganese dope C24 nanocage showed best catalytic activity for the rest of the studied first row transition metal complexes. Let's focus on the catalytic activity of the manganese catalyst for the hydrogen dissociation. Initially, hydrogen gas adsorbs on the manganese catalyst with a favorable binding energy. Hydrogen-hydrogen bond length at intermediate stage is slightly stretched compared to the hydrogen molecule in an isolated state, indicating the activation of the hydrogen molecule. At the transition state, dramatic increase in the hydrogen-hydrogen bond length is observed, revealing significant weakening of hydrogen-hydrogen bond. In the product, hydrogen-hydrogen bond length further increases, reaching 2.39 angstrom, which demonstrate that hydrogen-hydrogen bond length is completely dissociated. Therefore, it is concluded that manganese dope C24 catalyst effectively promotes hydrogen dissociation through a process called homolytic cleavage. To visualize and differentiate between the shared shell and closed shell interaction, non-covalent interaction analysis is performed. NCI analysis consists of two descriptors, reduced density gradient and product of the density and second value of the Laplacian. However, the types of the interaction depends on the sign and value of lambda 2. If the lambda 2 is large and negative, this indicates electrostatic interaction. If lambda 2 is negative and close to 0, interactions are van der Waals in nature. So, absence of the spikes at low density gradient reveals the interaction between the hydrogen metal and metal carbon in the hydrogen doped C24 complexes, which reveals that these interactions are the covalent in nature, which is perfect for the catalysis reaction. Electron density differences. In addition to above property, we also employed electron density differences analysis to understand the charge transfer between the hydrogen and metal complexes. Isosurfaces obtained from EDD analysis is characterized by the purple and blue colors. The blue color isosurfaces showed the depletion of electron density, whereas purple isosurfaces indicate the accumulation of the electron density. So, appearance of the both types of the isosurfaces indicates the exchange of the charges between the hydrogen and metal complexes. The table presents the NBO analysis for the hydrogen, transition metal and carbon atoms of C24 attached with the transition metal atoms. The positive sign of the NBO charges on the transition metal atoms indicate that charge is shifted from transition metal to hydrogen and carbon atoms. Among the studied transition metal complexes with the adsorbed hydrogen, the highest charge exchange is observed in the manganese complex, which is consistent with its low hydrogen dissociation barrier and high interaction energies. Reaction pathway for the hydrogen dissociation on the transition metal dope C20 complexes. We also study the hydrogen dissociation on transition metal dope C20 and C60 nanocages by adopting the same strategy as in case of C24. The lowest dissociation barrier is observed in transition metal dope C24 complex is for the zinc with the energy barrier of 0.53 electron volt. The lowest dissociation barrier in the transition metal doped C20 catalyst is observed for the scandium. Although scandium doped C60 complex showed the better catalytic activity than the transition metal doped C20 catalyst, however, it is not as effective as the manganese doped C24 catalyst. Therefore, we conclude that manganese doped C24 nanocage is the best catalytic surface for the hydrogen dissociation compared to the transition metal dope C20 and C60 surfaces. Conclusion: the doping of the first row transition metal over the selected nanocages is thermodynamically a feasible process. C24 is suitable a substrate for the single atom catalyst as compared to C60 and C20 nanocage for hydrogen dissociation due to higher thermodynamics stability. Whereas transition method of C20 catalyst comparatively showed poor catalytic activity for the hydrogen dissociation. Results obtained for our designed catalyst are comparable with that of the state-of-the-art platinum-based reported catalyst. Thank you for your attentions.